I want to finish this up, and then we're going to move into dynamic Bayesian networks. So belief propagation, as you recall, it's like a circle of telephone, and it's probably one of the most powerful things that we can do with a graphical model. So if you have a model and you have describes different variables, and somebody comes into the ER and they have certain variables, what we want to do is we want to input those variables into the model and then update the beliefs or the probabilities of the other pieces. So the idea is very similar. These things are going to talk to each other, and they're not going to do it over the graphical model. They're going to do it over a cluster graph, and that's where we kind of set out. We talked about cluster graphs. This is an undirected graphical model. This is the cluster graph, and then we have got cliques, and then we've got separators. And these kind of talk about how things move between each other. A and B connected to B and C, and B is on the separator. So that's their common points. And it doesn't have to contain everything that's in the intersection between the different cliques. And then, yep, please come on in. That's okay. It's been getting loud in the hallway with the different thing going on in the foyer every day. So that's where we left off. And we talked about message passing. You know, we pass between cliques on this object. 2 can pass to 1. 1 absorbs what it knows, and then it passes a message to the other clique, and so forth. And you go kind of around the horn. The original algorithm we discussed, there's more. First of all, there's more than one clique graph or cluster graph for a given distribution. And in this case, we're talking about factors here. These are not probabilities like in the Bayesian network, but we can do different types of assignments to cliques, and we can even write a completely different tree. This is not a tree, a cluster graph, if we want to. And we talked about the algorithm and some problems with it, namely that it's not necessarily going to converge. And that was kind of an issue, and it was a little bit sticky to get that. And we said, well, if we're in another situation where we can write the cluster graph right here this is a graphical model, this is the cluster graph. If we can write it as a tree, we're in better shape. Okay? And so there's certain conditions for which we can do that. And the point that I made that I wanted to stick last time was that if you have an undirected graph, you're not necessarily going to be able to get a tree. This is undirected. This is a tree. It doesn't look like a tree, but our definition of tree here is very loose. It just means there's no cycles. Okay? So with the ones that we talked about before, if there was a cycle in the clique tree or the cluster graph, by the design of the algorithm, you have to pick a random piece and whisper your message and so forth. But depending on where you start and where you end, you could come to different solutions. Still valuable, okay, because everything is kind of in proportion, but it's not going to be exact. And so then we said, well, an undirected graph may give rise to a cluster graph that has cycles. We just saw 3 of those, okay? And I said, well, it could also give rise to one that does not have a cycle. And when it does not have a cycle, we're in a better situation, okay? A Bayesian network will always give rise to a cluster graph without a cycle or a tree, okay? So that's a very useful property. And in this scenario, we already went through these slides. I'm just kind of recapping, but there's a forward pass and a backwards pass. And we can start at the leaves. We call them the leaves of the trees, which are kind of the end pieces, forward and backwards. And we can query beliefs for different things, and we can see that it is just, if we think about the products here, it can be written simply as a product of potentials. And we're marginalizing over the variables that we don't know anything about. So we recall that was analogous to, you know, talking about Aunt Thelma and your office friends. You don't talk about the same people because they don't know each other, right? You only talk about people that you know. So the marginalization, going back 2 weeks ago to when we talked about marginalization for probabilities, the same idea. And so we can go with that. And we formalized this, and we talked about more complicated matters. We talked about a couple properties. One was the running intersection property, which said essentially if X appears in one click and it appears in another, then it had better appear on the separators that connect them. Okay? So that's one property. We hashed this example about grade and SAT and letter and job, and this is more enriched. We put this Bayesian network. This was the first Bayesian network that we had talked about in terms of the click tree, and we had written this out. An assignment of probabilities is the same as it was before, where we did the assignment of factors. Remember, the probability is just, the conditional probability is a special case of a factor. So we still make the assignment in the same way. And we can also kind of see where these different clicks are. C and D, GID, GSI, GJSL, that's GJSL, that's this piece here, and HGJ. So why did I do that? Well, you might say, how do you come to this? How do you go from here to here? There's a lot of different steps that go in that process. Inferring a click tree from a cluster graph, you'll see an example that I'll do later. For doing that, you won't be responsible for that. That's a difficult challenge. But I want you to kind of see that the shapes, although it's not a direct translation, you can kind of see how the local families map in the different clusters. It's not an obvious assignment from just inspection, but we can see that the groupings in the graphs are somewhat mimicked in the clicks. This is the belief message passing piece. It's the same idea that we talked about before. We also discussed a property called correctness. And if we kind of, if we have information about X here, we know it has to translate through the separators. If it's going to be in any click here, it better be on the intersection and the clicks between them. But we also kind of have a situation where any message passing will not concern X. Going from 3 to 5, there's no talking about X because it's not in 5. Okay? What does that mean? It actually means something important, because when we want to query on networks, if we're querying, if you think about the way that this translates into this type of feature, this type of tree, certain queries are not going to be impacted, not going to impact other areas of the graph. So sometimes you're going to say, okay, well, X is equal to 5, whatever X is. X is, I don't know, 5 is kind of a weird number. I don't know what 5 could stand for. But you get a measurement, and your HDL is, actually, I'm not even sure what that would be, 65 or something. X is 65. Okay, you've got your HDL measurement. So what's happening here? Well, those variables that are contained in 6, 4, 3, and 7 are going to be impacted by knowing that information. But whatever's contained in click 5 and click 2, they don't care. Okay, so information changes, but not all information. This also relates, although we won't hash out the relationship completely, it relates to the idea of, what was the term we used for it? Probabilistic querying and causal, evidential, and intercausal reasoning. This also, so this piece here, we talked about deseparation and deconnectivity. These are actually deconnected in the graph. They end up being deconnected. So those are the only ones that can be influenced by such information. Okay. So we do get exact properties out of this. So in the order, it doesn't matter. It's not as sensitive as the one we talked about with cycles, where it depends on where you start and which ones you pick up. Now you can start with any leave. And simply, if I start with 2 and I whisper to 3, 3 has to wait for all of the messages before it can talk. So we'll start with other leaves, and we eventually get all messages and then go the other way. So this is where we left off exactly. How do we actually work with the clicks? And you have experience doing this already, although you haven't been tested on it in your homework assignment. You will be. We can do things in a couple of different ways. Now we're interested in inference. One thing we can certainly do is do probabilistic queries on variables. What does that mean? That's essentially looking at the conditional probabilities, multiplying down the tree, that kind of stuff. It doesn't take into account any new evidence. So it's essentially you fit a graphical model from the data, you fit a Bayesian network, and now you're kind of looking at the different paths. Okay? So if you have competing paths, for example, you can compute the conditional probabilities by just multiplying down the tree. And we can also look at different states and so forth. That's just using information within the graph. The next thing is to think about if you introduce new evidence. So here, z is equal to z, little z, as some state. It could be a state or it could be a continuous variable, depending on what type of data you have. And you want to query x. There's a couple of cases that could happen. One is that if x appears in a click with z, okay, then essentially what you do is simply, in the language of clicks, multiply the click that contains x with z with an indicator function and reduce the evidence. Sum out irrelevant variables and renormalize. So we take in new information. It's exactly like the marginalization that we showed a couple weeks ago. You set a state, okay? So this person has genotype heterozygous, okay? They're heterozygous, and now I know that information. Now that's going to change what I know about X. And they appear together in the click. It's actually makes sense because of the way the local models are assigned. So it's a reduction of evidence, okay? The other case is more interesting. This is kind of obvious. You could do this, pretty simply. It doesn't really require any propagation because we're thinking about z, entering evidence z, and we want to know about x. And they're probably in the same model or close to it. So it's just a basic, the same local model. So it's very basic. It's a matter of marginalization. Case 2 is more complicated. If x does not appear in a click with z, we still have to absorb the information into the click where z is. Okay, so essentially, we're resetting the state. Okay, so if z is in here, right, and x is down here, then I still have to absorb this information in here. And then I essentially just do the message passing, forward and backwards just like before. Okay? And so what will happen is that anything passed from this will change. Okay? So now this click, if z is in here, and z can be in more than one click. Z could be here and here, right? But any click that contains z, the variable that I have evidence about, takes in that information. Okay? It absorbs it. And it changes the whispering in the message passing algorithm. So that's how that changes. And eventually, because of that whispering, if x is sitting down here, that is updated. Okay, that changes. And so that is the way that we do that type of reasoning. Change the message and pass it on. Okay? All right. So now I will go through, so let's see. Oh, this was just an example, a simple example. Set evidence in A and query D. Essentially, remove all evidence that is inconsistent with A, so it's a marginalization. Absorb evidence into the first one and pass it along. And the way it's going to be passed along, where it's changing, this message is changing on the forward pass. So that information that we know about D is now changing. So it's pretty straightforward. This is an example. Another, I want to show you this because, well, it's from my own work, but it follows the example I showed you before. So in this particular example, let's just look at part A. So this is an example of the conditional Gaussian Bayesian network. Okay? These are discrete variables in the boxes, and these are continuous ones. And so that is your graphical model, right? That is the graphical model. It's a little bit simpler than this one, but it's a little more complicated at the same time because it has discrete variables in it. Okay, so I just want to give you an idea of how you can go from this piece here to this one and what that involves, okay, and how to do some querying. You'll have lots of opportunity to do querying. I think it's one of the most important pieces, but I won't. Doing the inference of the click tree is more complicated, but I'll show you here kind of some of the different steps that have to happen. And a lot of this is rooted in graph theory. So the first thing is you take your input. This input is actually your graph. And there's some things that have to happen. We call the first step of this triangularization. And in that step, what you'll notice, what's different, is that the directionality of the edges is dropped and the parents are married. Okay? So if you look at this, you see that it's completely undirected, and then you'll see that these red lines kind of marry the parents for the different ones that aren't already married. So for example, X1 has Q1 and Q2 as parents. So in this graph, it's no longer directed, and now I'm drawing a line between Q1 and Q2 because I'm marrying the parents. Then there's another phase of this where you have to make the graph strongly decomposable. And that is a more challenging piece, but you essentially look for situations that violate some of the properties for exact inference. So I'm not going to talk about those properties today, but I just want to show you the path here. Once you're here, you can go to a junction tree, okay? And it is essentially a factorization of the strongly decomposable piece. And there are some conditions that also have to be met. So there's lots of steps in the process. But this is an example of a real junction tree. And it has, in the clicks, just like before, the different variables in the models, and we also have separators. And so what you want to do, so this is just to give this appreciation. You've got an initial network, and you want to absorb information about such a network and different nodes and make predictions about other things. This is what a junction tree looks like. Getting to that junction tree is complicated, okay? But we do all of our operations on the junction tree, but actually we try to understand the output in terms of the original graph. So in this particular example, what I'm showing here is, let's talk about a network which has genes and genotypes, and I have information about this gene here, whatever that information is. I have it, it's just called an absorbed node, but it could be a knockout, it could be that it's overexpressed, it could be anything. And so if I have that information, I should be able to understand what's happening with the other things in the graph, or what's most likely happening. Okay? And so this gives a scale for doing this. If I have this information, I can predict these genotypes. So I can predict what genotype state I most likely come from. I can also predict what the states of the other variables in the network are. If I look at this picture, all I can see is that it's connected. It's the parent of these guys. It's, it has QTL here and so forth. But it's not informative in the way that, we usually want to think about. So usually, if I'm designing such a network, it's for a collaborator that wants to do something with it. They want to do an experiment. Okay, so in that experiment, they might say, well, can we target this one? If we target this one, what happens? Okay, so that's the kind of thing. And then this is the result of the belief propagation. And so we describe that actually. I don't have it written here. We wrote it in the paper. But we describe it as assigned Jeffreys information. So it gives actually an idea of how different things change and if they go up or down. So this is a real network. This was targeted -1, so down-regulated. And now we can see what changes. Okay, so if I push this down, so I took a data set and I figured out what the network should look like, step 1, which you guys know how to do. You identify a network. Step 2, let's do something with it. So what if I change this? What if my collaborator wants to do an experiment where I change this gene? Okay, I'm going to knock it down. But I want to see, is that a dangerous thing to do? What's going to happen to the rest of the things in the network? This is essentially telling us, using belief propagation, this gives rise to a tree. We do operations on the tree. And we think about looking at the impact. So you have your network, and you have what happened to it. How did it change? And you'll have exercises to do with that in more natural networks like disease networks and so forth. But we can see that, well, if this is -1, then these all go down. These all go up. Okay, so you get an idea for how the balance changes. And we can also think about that over a spectrum of evidence. So this is the -1 that I showed you before, but also I can take that and I can see the trajectory of the different pieces of the network over a whole bunch of evidence. And if I also take into account the fact that the network is uncertain, I can do this in a whole bunch of networks and see how stable the predictions are. You can also think about 2 changes in a network. So I want to change this one, and I want to change this one. And I can change them in different directions. Of course, viewing that requires a 3-dimensional surface, but you might not want to view it over a spectrum. You might say, and you'll have to do, I hope that you'll have to do this. I'll have to check the next assignment, but you might have input. You know that the SATs are strong. You know that the course is difficult. Go to the junction tree, put that information in, propagate it, and then figure out how likely the letter is strong, and so forth. Okay, so that's simply updating the query. So in conclusion, we can use the click trees to compute the exact probabilities or marginals. Okay, marginals are exact. They can be computed with a forwards and backwards pass over the click tree. We can propagate evidence and answer queries in a computationally feasible manner. We don't have to do that loopy exercise that I showed you before. So every single Bayesian network has a click tree. Okay? We can compute exactly on the click tree. Undirected graphs. Sometimes they have a click tree, sometimes they don't. Okay? And that is how we make predictions. One of the ways that we make predictions.